All right, welcome everybody. Today we are going to take a look at a Atwood's machine. And what we're going to do here is we're going to use this to do what our big goal for this unit is, or one of the big goals, which is analyze data to support the claim that Newton's second law of motion describes the mathematical relationship among the net force on an object, its mass, and acceleration. So this is the cause and effect. And let's see what we know already. We know that we can analyze and measure motion using, let's see, we could use a ruler and a stopwatch. We also saw that we could use a motion sensor. And we've also used photo gates in this class. And we've done most of the analysis of our data in Google Sheets by looking at graphs that we've made. And we've seen a bunch of different relationships between variables. You guys really know we did that whole patterns lab. And so one of the relationships that we saw is that you guys actually did this in the patterns lab. We had a, with F equals ma, you saw that if we change the mass and measure the acceleration of the Atwood's machine, was actually what we did, a modified Atwood's machine in the lab, we saw an inverse relationship between acceleration and mass. And but we've seen tons of other ones. We've seen linear, we've seen quadratic, we've seen inverse squared. So today we're going to take a look at an Atwood's machine, and what is the acceleration of the system is our main goal. We're going to use physics words to describe the motion. Okay, so well, if I was to bring this mass down and then let go of it, what would happen? Well, it's going to accelerate, and it's going to accelerate around this pulley and down this way. So we can't really say it's accelerating up or down unless we determine which mass we're talking about. And usually we'll have like M1 or M2, and then we can say, well, mass 1 is accelerating downwards, M2 is going to be accelerating upwards. So we're really looking for acceleration. We're having a massless string, a massless pulley. We're saying no friction and no air resistance. So we're going to try and really simplify this Atwood's machine to figure out this acceleration. What is the acceleration of the system? Again, that's what we're trying to do. Draw a free body diagram for each of the masses. So on mass 1, my free body diagram, let's see, what is on here? Let's see, it is definitely in Earth's gravitational field. So I have the force of gravity going down. And now what's going up? Well, that's going to be the force of tension. And it's going to be smaller, and I know that because M1 is going to accelerate downwards. So I'm going to call that the force of tension. Now for M2, because it's on the same rope, we're going to say that it has the same force of tension. So I have to draw that about the same as much as possible. Force of tension here. I'm going to say this is Fg on mass 1. And then I have this one, which is going to be Fg on mass 2. Now I set up these free body diagrams with my vectors so that I can now analyze the system and see what's going on, and then from that I can figure out the acceleration. Determine which way it is accelerating. Make that way positive. Okay, well I know mass 1 is going to go downwards, so it's going to be accelerating. Let's see, mass 2 is going to go up, it's going to go around and down that way. So I'm going to call that direction positive. And it's weird because the direction goes around a bin, but you could imagine if we had mass 1 and I had mass 2 connected to a string, and I could accelerate them this way, and I could call that all positive if I wanted to. So we've got that positive direction. Now, do the sum of the forces equal 0? No. And we know the sum of forces don't equal 0 because it is accelerating. And if we have acceleration, if there is acceleration, then the sum of all forces is not equal to 0. Therefore, what does the sum of all forces equal? Well, the sum of all forces is going to be equal to, well, mass times acceleration, right? And in this situation, specifically, let me make sure I'm not jumping those, the sum of all forces is going to be equal to, well, let's see, we called this direction positive. Ooh, that's cool. And we said that I had Fg of m1 going this way. I had my Ft m1 going that way. We actually didn't say it's m1 because the Ft is the same on both. And then I had my m2 downwards, Fgm2, and I had the force of tension upwards. Okay, so let's look at the sum of all forces now. And I'm going to use this positive acceleration to determine which vector is positive and which one's negative. So if anything in this direction, I'm going to call it positive. So Fg, the force of gravity on mass 1, is going to be positive. Shorten that to Fg1. This force of tension is going to be negative. This force of tension here is going to be positive. And this Fgm2 is going to be negative. I'm just going to call it Fg2. Now we can see what happens here. Oh my goodness, Ft minus Ft plus an Ft, gonzo, get out of there. So now we are left with the sum of all forces is equal to Fg1 minus Fg2. Okay, let's go see what's on the next page. I feel like I'm going to need this. Let me copy it. Okay. What are the sum of all forces? Well, we found the sum of all forces are going to be equal to Fg1 minus Fg2. And so we're going to make those equal to that Ma that we saw before. So Fg1 minus Fg2 is going to be equal to mass times acceleration. Oh, cool. That's all right. Now, never forget the mass in F equals ma in an Atwood's machine is the system mass. Ooh, that's helpful to know. What is the mass of the entire system? Well, the mass of the system, actually I usually just write that as msys, mass of the system is going to be equal to m1 plus m2. Those are the objects that are being accelerated. Sure, there's a pulley. Sure, there's a roof. Sure, there's a string. I'm not worried about those because I have a massless string. I have a massless pulley. I'm not worried about any of that. I'm just going to say m1 plus m2. Now we can solve for acceleration. So let me bring all of those things down. We had the sum of all forces was Fg1 minus Fg2. And we had that equal to mass times mass of the system times acceleration. So now if I want to solve for acceleration, acceleration is going to be equal to Fg1 minus Fg2 divided by the mass of the system, which was m1 plus m2. Cool. So that is how we are going to analyze a Atwood's machine. Here's some follow-up questions we can go through. When will the acceleration be closest to 0? Well, if I have m1 equal to m2, it's not going to move. Or it could move at a constant velocity. So the closest I get to m1 equals m2, the closest it will be to 0. So get close to m1 equals m2. Could the acceleration be 0 meters per second squared? Sure. If we had m1 is equal to m2, then the force of gravity on 1 would equal the force of gravity on 2. The sum of all forces would be equal to 0. And then that means we could have either it's not moving or we're at a constant velocity. So yeah, there could be of constant velocity if m1 was equal to m2. What two situations could this be in equilibrium? Okay, well, we defined equilibrium the other day as when the sum of all forces is equal to 0. Again, this would happen at a constant velocity. Or when the masses aren't moving. When will the acceleration be closest to 9.8? Okay, well, let's think of the opposite of that, right? If we were to make this mass 1 huge, super heavy, and mass 2 was mass 2, well, it's going to accelerate, but way faster. What if I made mass 1 huge and I made m2 very, very small like a feather? well, then we're going to get really close to 9.8 meters per second. So when M1 is much bigger, two alligators, that's actually a real sign. Two alligators means much, 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 much bigger than M2. Could it ever accelerate faster than 9.8 meters per second squared? That's almost like a philosophical question. Well, I guess if we were on Jupiter, but then you would fall through Jupiter's gas and die, so I don't think that's a good way to do it. I guess we could be on a heavier planet, but you'd really have to be on another planet to get that faster, or have some kind of external force pushing on it. So only in special situations. Like an external force or more massive planet. Number time. Oh boy, numbers. Here we go. Okay. If I had mass 8 kilograms, mass 1, and M2 at a mass of 2 kilograms, what's the acceleration of the system? All right, well, mass 1, that's going to be equal to 8 kg, and mass 2 is equal to 2 kg. Okay, so if I drew my free body diagram again, I'm going to do pro level free body diagram, where I'm just going to go. Okay, well, now I have Ft and I have Fg. Here, Fg is going to be equal to mg. So Fg is equal to the mass, which is 8, times gravity, which is 10. So my force of gravity here is going to be 80 newtons. Don't forget your units. Mass 2 is going to be my Ft and Fg2. 1. Let's see. So that is Fg2 is equal to the mass, which is 2, times gravity, which is 10. Fg2 is equal to 20 newtons. And my equation from before, we said acceleration, which is a vector, is going to be equal to Fg1 minus Fg2 divided by m1 plus m2. Those are also vectors. Mass is not a vector. Okay, so let's do this. I have acceleration is going to be equal to 80 newtons minus 20 newtons divided by the masses added together, which is going to be 8 plus 2. Oh boy, look at this. This is going to work out nice, I think. I get 60 divided by 10. My acceleration is equal to 6 meters per second squared. Awesome. Good stuff. Graphing time. Oh boy. What would the following graphs look like for the accelerated motion of an Atwood's machine? Well, we saw when you guys were doing 2.2 that if I have a constant acceleration, that means my velocity versus time graph is linear, and my position versus time graph is quadratic. And it's accelerating, so it's going to follow those same rules. And I believe that's it. Awesome. I look forward to seeing your learning. Please ask questions if you have any. Bye-bye.